Hi guys, this is Utku again. When we recorded the video, for some reason my introduction was not recorded. That part was cut out. So instead I'm doing this voiceover. The video will begin now. And today I'll be doing a video in the Learning Class Studio in Digital Humanities Center. And thanks to them, we're able to get this room with a better camera and better lighting. Hopefully it'll be a better quality video. And I'll be doing a fluids problem using Reynolds transfer theorem, angular momentum, for angular momentum. And we have a sprinkler here, and I'll just explain the diagram real quick and then we'll get started. So in the diagram, I have a sprinkler. The Q in is telling our, it's the flow rate in to the sprinkler, and it goes from the center out to the each arms. The area of the arm is 0.3 centimeters squared. It's the same throughout, it's uniform. And the exits are 20 centimeters away from the center. And we're asked to find the torque to hold the sprinkler in place. And I'll just go over the Reynolds transfer theorem, angular momentum equation really quick. So it states that the sum of the torques is equal to the differential of this integral with respect to time. The integral is the boundaries are with respect to control volume times, and within the integral is going to be rho times r cross v times d volume plus the integral of rho times r cross v times v dot product n times the differential area with the boundaries control of the control surface. Alrighty, so the box here around the sprinkler that I drew is the boundary for this problem, and there's red right here. These red arms are our R vectors. Those are the lever arms. That's what they are. And the velocity, the water is shooting out this way and that way, which creates the torque. Alrighty, so let's see. So look at this equation. Oh, before we get started, this part of our equation goes to 0 because it's steady flow. During steady flow, that part always goes to 0 in any RDT. So we'll just be focusing on this one, which will say sum of the torque will equal integral of control surface rho r cross v dot n dA. Oh, also I forgot to mention our n's. If you can see them, they're right here, right under the v. They're parallel, direct next to our velocity vector. So it just says that this part is just going to be 1. It's going to equal 1. Alrighty, so I'll use pink. Okay, or blue. Alright, so look at this equation. Rho, we can find it, no problem. R, we already have 20 centimeters. N is not a value, so we don't have to worry about that area. We already have that area. So all we're missing here is our velocities. So let's get the velocity. So we know that the flow rate is equal to velocity times the area. Although in this case it won't be a vector, but velocity times area. So if we solve for velocity, we get flow rate over the area will give us velocity. So if we plug in our values for this, we will get 1,000 centimeter cube per second divided by, hopefully that's visible, that is 0.3 centimeters squared. This will give us 1,667 centimeters per second, or 16.67 meters per second. Perfect. I'm going to write this on this side so we can use this part of the class. Perfect. So we said that velocity is equal to, oh, come on, man. It's equal to Q over area, which we said is equal to 16.67 meters per second. Perfect. So now we have our velocity. All right, let's now write our RTT for this problem. So let's go right here. Sum of the torque is equal to summation of the left side of, because we have one exit here, one exit there, so we have to have this one for each one. So one left, one right. So the left is going to equal rho r cross v. So our r is, these are our r's, our lever arms, and our velocities are right here. So if we just take a look at this part, the right side, we'll see that our r is coming in this way, and velocity is going perpendicular, or straight up. So it's perpendicular, and it's 90 degrees. So the angle between them is 90 degrees. So we can go right here. We can just say r cross v. Is that visible? Yeah, that is. Okay. I'm just gonna read it though. R cross v is equal to magnitude of r, magnitude of v, sine of theta, which is this theta is the angle between r and v, and we just said that it was 90 degrees. So sine of 90 degrees will give us 1, so that the cross product just gives out rv, magnitude of these. So we'll just write r v dot n, the dot product of v dot n. So we know that a dot product is the same thing as magnitude of one multiplied by the magnitude of the other. Even though our n is just a normal vector, it's just the value of 1, times cosine of the angle between them. Oh, come on, please. Is that visible? No. Okay. Time to change markers. Hopefully this one is better. There we go. Cosine of the angle between them. Yeah, we'll go with green from now on. And I'll rewrite this here. But before that, the theta, angle between them. So if we look at v and n, we see that they're parallel, so the angle between them is 0. Cosine of 0 goes to 1. So we just get that this is equal to Vn, but n is 1, so it's just equal to velocity. And it's positive because they're facing the same way. This one. Perfect. So let's just rewrite this really quick. We'll get back to our question. So the sum of the torques is equal to the one on the left, rho Vr, or Rv, however you want to. Let's just write Rv for all the same. There we go. Rv times, again, same thing, just velocity, dA, plus the integral of right side, rho, Rv, again, same velocity right here, positive, I forgot to put the positive here, dA. And then we can say dA right or left, but same area, so I'm not going to bother with that. Now, if we just put these guys together, well, from this, we will get rho Rv squared A. From this guy, we're going to get rho Rv squared A. So we get the same thing on both sides. So the sum of the torque will equal 2 rho Rv squared A. Now, if we just plug in our values, we will get 2 times cube times, we just said this was 20 centimeters, so it'll just be 20 times 10 to the minus 2 meters. Velocity, we said it was 16.67 meters per second squared, times our area, which is 0.3. So here's a funny part, it's in centimeters still. So before, actually, I have to do this. Let's just convert that to meters really quick. I can do it right here. And this will give us 3 times 10 to the minus 5 meters squared. Perfect. And this will equal 2 times 1,000 times 20 times 10 to the minus 2 times 16.67 squared. squared times our last answer, and we get equal to 3.34 Newton meters. Perfect. So that's the torque on the water. That's the torque that the water is going to create on this guy. Because it's positive, it's actually going to be going this way, clockwise. So our T hold should have been drawn the other way, so like this way. This will be our T hold, because the T hold needs to counter the torque from the water, which is going clockwise. So our T hold is supposed to go counterclockwise. So this is equal to the sum of the torque, and our T hold will equal negative 3.34 Newton meters. And that's our answer. But before I let you guys go, let me erase this part, and I'll just want to draw the free body diagram for you guys, just so you guys can see it better. Just hold this better as well. Alrighty. Okay. Just do a quick dirty one. Oops. It's too much. Come back. Okay. So we said our torque the torque of the water, the sum of the torque, was going clockwise at 3.34. Oh, you guys can't see that though. Oh man. Alright, let's just draw that a little bit down here more. Alright, perfect. That's a little bit better. No, it's not. Oh my. Okay, lower. That should be good now. Perfect. So this was the sum of the torque, which we said was 3.34. So our torque hold is going to be going this way in order to counter that torque and keep it stationary. So that was a question. It was a nice easy one for RTT of angular momentum. And I'll see you guys on the next one. Thank you guys for watching.